Hey everyone, welcome back. This is part 2 of a 2-video series where we're going to talk about how derivatives relate to velocity, position, and acceleration. And so right now we're going to be looking at a graph and how we can pull information from that graph about the motion of a particle. Remember, this particle is just moving along a number line. It's like a bead on a string going back and forth, having different speeds and velocities and directions. And so we're going to look and see if we can relate a graph, which is just a picture of the scenario, to what's happening with its velocity and position and acceleration. So let's take a look. So first thing I'm going to do anytime I'm given a graph, especially on an AP exam, is I need to make sure I pay attention to what that graph is telling me. And I'm going to write down some extra information along the way. Every time I see a graph, I'm going to relate it to its derivative or to its original function. So this is a velocity graph. So I'm going to make this note and I'm going to say this is velocity. It's also the derivative of position. Okay, so I'm going to say this is s prime of t, s being my positional variable. So let's describe what we see here. So as I go along the time second, right, so this is meters per second, so my velocity here is positive. That means I'm moving forward. So I move forward from times 0 up through time 3 because the velocity is positive. Even though the velocity turns around and goes down, I'm moving forward. So I'm going to say I'm moving forward or to the right. That could be it if you'd rather. Let's use that because we like our number lines. So I'm going to be moving to the right from t equals 0 to t equals about 3. Now, during that interval, you'll notice that my velocity goes up. So my velocity reaches 10 meters per second. But then after that, it decreases. So it speeds up from t equals 0. It looks like to about t equals 2, then slows down. Now, let's see what else is happening. So at some point, I reach a velocity of 0. At t equals 3, we stop. Okay? And then what happens is the velocity becomes negative. So let's recall what that means. When we have a negative velocity, it means the particle has turned around and gone the opposite direction. So I'm going to make a note of that. Stops and goes to the left. Now, anytime it's living in that negative land, you can see that it stays negative pretty much for the rest of the graph. During that entire time, that particle is moving to the left. Now, just because the velocity is going up and down doesn't mean it's changing direction. It doesn't change direction until the velocity changes from positive to negative or negative to positive. So we have it moving to the left forevermore, well, until 9. We'll talk about what t equals 9 is. So it stays down and it stays negative until t equals 9. But let's talk about what's happening. From 3 to 5, t equals 3 to t equals 5. Look at what's happening to the velocity. My velocity goes from 0 to negative 15 meters per second. Now remember, speed is the absolute value of velocity. So the speed here is positive 15 meters per second. So I hope that you can deduce that this means that my particle is actually speeding up. So from t equals 3 to t equals 5, it speeds up. And then at, or I guess we'll say from t equals 5 to t equals 8, let's look at what's happening. My velocity stays at negative 15 meters per second. So my velocity stays constant. So the particle is still moving, it's just moving at a constant speed. Now from t equals 8 to t equals 9, let's check out what's happening. My velocity goes from a negative 15 meters per second, a speed of 15, and it drops all the way back down to a speed of 0, okay? So the velocity actually decreases and we slow down. Now we're still moving left. Remember, the negativity of the velocity just tells you what direction are you slowing down in. So anytime we're approaching that x-axis, we're going to be slowing down on a velocity graph. So that's something to keep in mind, that just because velocity is negative doesn't mean we're going slower. So we just answered all of these questions And we talked about when the particle is at rest. So at t equals 9, it stops. And it just kind of hangs out there. So we kind of addressed when we're moving forward, backward, when we're at rest. One of the things we want to think about though, and I referenced this multiple times, is the speed. And so we wanted to take a look and see what does this look like if the graph showed speed instead of velocity. So essentially, if I take what is shown here and I sketch it on, all the speed does is take the velocity and turn it positive. So I'm still going to have this same little peak that looks like this. It's still going to come down to 3, but here's where it's going to be different. Essentially, any negative values flip up and turn positive. And the easy way to take this is to say, well, any negative velocity, if I just reflect it about the x-axis, I've created a speed graph instead of a velocity graph. So essentially, this goes up to here, it goes up to 15 actually, and then it comes back down to 9. It's flat, and then boom. So the speed, all it does is take any negative portions of a velocity graph, reflect it up and over on top of the, into the positive land, reflected about that x-axis. Now let's talk about acceleration. So if I want to sketch the acceleration, and I've included the velocity graph here so we can really see what's happening. If I look at my acceleration, to graph the acceleration, remember the velocity is the derivative of position. Acceleration is the derivative of velocity. So remember, derivative is slope. So all I'm going to be doing here is I'm looking at the slopes of the velocity curve. So let's do this. For this chunk right here, I go up 10 over 2. This has a slope of 5. So my acceleration throughout this segment is 5. And remember, when we graph a derivative, if the endpoints are closed, that means we consider it to be differentiable at the endpoints. But anywhere we have a sharp corner or a cusp, remember the derivatives as we approach that spot from the left and the derivatives as we approach that spot from the right have to be approaching the same value. And here, anytime we have a sharp corner, that's not going to happen. So what I'm going to do is from 1 to 2, so from 1 to 2, my acceleration will be 5, and I'm going to have an open dot on the interior because that corner is not a differentiable spot and the acceleration doesn't exist. So now for this next little chunk, notice this little line segment is very constant, and even though it dips into negative, the slope remains the same. So from 2 to 5, I'm going to find that this slope, let's see, I went down 25 and I went over 3. Ooh, that's ugly. I don't like that number, but we're just going to deal with it. So negative 25 thirds is roughly, what, like 8 point something? So negative 25 thirds, 8 1/3, negative 8, right about there, and 1/3, from 2 to 5. Yikes, that was ugly. Who picked these numbers? Now, here my velocity is constant. If something's constant, it means the rate of change is 0. So the acceleration here is going to be 0. So from 5 to 8, I'm going to have acceleration being 0. And then from 8 to 9, let's see, I'm going up 15 over 1. So my slope is a positive 15. And then after that, let's use an open dot. After that, we're back down to 0. And it kind of goes on forever. There's no acceleration because the particle's just kind of sitting there doing nothing. Now, one thing that I want to relate for you here is this concept of when am I speeding up and when am I slowing down. Now, looking at a graph, it's easy to see. As we approach the x-axis on a velocity graph, we're speeding up. As we move away, or sorry, as we approach the x-axis on a velocity graph, we're slowing down. Let me say that right. As we move away, we're speeding up. So we can see, and I'm going to erase some of this so we have a little fresh canvas. So it's really easy to see that as I'm moving away, you know, my velocity is increasing to 10. So here my velocity is increasing, and then it decreases and approaches the x-axis, it's going down to 0. and then it speeds up again because it's moving away. We can see that really easily when we have a graph. But when we don't have a graph, when all we have is numbers and information, we need to understand the relationship between the acceleration and the velocity to be able to tell when something is speeding up. So let's take a look and write a few things in. Notice here, I'm going to make a note. I have a positive velocity here. I have a positive velocity here. I have negative velocity here. Negative velocity, and I'm not going to worry about where I have zero velocity. Now what I'm going to do is I'm going to take note of all of the acceleration and whether the acceleration is positive or negative. So when I look at this, remember acceleration is your slope. So for this first chunk, I have a positive acceleration because the slope is positive. And when I scroll up, sure enough, between 1 and 2, I had a positive acceleration. But then here in this little chunk here where I have this positive velocity, here my acceleration was negative because the slope of that area is negative. And you know what? It's also negative down here. And then as we go here, we had A was 0. But then this little chunk has a positive slope. And if you look between 8 and 9, we had a positive acceleration up here. So here, I'm going to write down positive A. And now what I want us to do is just take note of when we're speeding up and when we're slowing down. So here my velocity is increasing, I'm speeding up. But then over here I approached the x-axis, so I was going down, speeding down, slowing down, slow down. That would be the way to say it. And then I turned around and then my velocity actually approached negative 15. My speed was increasing, so here I sped up. And then over here, I slowed down. So let's see if we can find a pattern here. So I sped up. I had a positive velocity and a positive acceleration. Over here, I sped up. I had a negative velocity and a negative acceleration. When I slowed down, I had a positive velocity and a negative acceleration. And then over here I had a negative velocity and a positive acceleration. So do you notice any sort of theme between when we were slowing down versus when we were speeding up? I hope you did. And I hope you noticed that when velocity and acceleration have the same sign, same, SSS, we speed up. Same sign, speed up. When the velocity and the acceleration have different signs, that positive-negative relationship, we're going to be slowing down. And it should make sense because not only is velocity directional, but acceleration is. And so if you're trying to speed up, if your velocity is positive, that means you're moving to the right. If your acceleration is negative, it means it's pulling you backwards. It's pulling you to the left. So acceleration is directional also. And when you're moving to the left, if your acceleration is positive, that means the acceleration is working on you, pulling you right. Your object's trying to go left. So it makes sense that if they have opposite signs, they're going to be working against each other. And ultimately, you're going to see a slowdown. So I hope that this has been a helpful thing for you. There we go, not hidden behind the little screen. I hope that this has been helpful for you in helping you understand the relationship between acceleration, velocity, and position in terms of how we see it on a graph. Remember, a graph is just a visual representation of what's happening with the equations. So if you need a refresher on the equations and what those look like, make sure I've covered everything. Make sure you watch part 1. But hopefully this is helpful to you, and I hope you have a wonderful rest of your time. And stay positive, stay encouraged, and remember, mastery is not something that's expected the first time through, and you should be thankful when you're faced with a challenge because that's an opportunity for you to grow and stretch and learn something new. So stick with it. You can do it, and you know what? You've got this.